Hello everyone. Today we're going to talk about open hashing or separate chaining. So we're going to explain this concept and this way of hashing using some examples. So assume that we have these 10 numbers. So the number of records that we're going to insert is equal to 10. And also we have a hash table that is equal its size equal to 6. So m is equal to 6. Now also we are going to use the modulus function, hash function. So means that h of k will be equal to the modulus of k by value m that we have here. So the first number is 5 and its modulus by 6 is equal to 5, so it's going to be inserted at the last location that we have here. Then the next number is 7 and the modulus 7 by 5 by 6 is equal to 1. So 7 will be inserted here. Okay, so let's also write the indexes here. So 0, 1, 2, 3, 4, and 5. So the next number is 9 and the modulus of 9 by 6 is equal to 3. So 9 will be inserted here. The next number is 1 and the modulus of 1 by 6 is equal to 1. So it means that it should be inserted at this location. But as you see, 7 is already occupied this location. So that's the concept that how we can do the open hashing or the separate chaining. So every item that you have here is actually a linked list. So it means that the number 7 it was the first node of a linked list of these things. So we have the 7 and then we are inserting number 1 at the end of this here. So number 1 is inserted. The next one is 6 and so 6 modulo of 6 is equal to 0. So 6 will be inserted here. The next number is 3. Okay, so modulo of 3 by 6 is equal to 3. But 9 already occupied the location. So again, similar to what we did for number 7 and 1, we're also adding this number 3 here at the end of this linked list that we have the number 9. The next number is equal to 2. The modulo of 2 by 6 is equal to 2. So, and the linked list is empty, so we're putting here without no problem. The next one is 17. And the modulo of 17 by 6 is equal to 5. So, and here the number 5 already occupied the location, so we are increasing, we are adding this to the end of the linked list that we have here. So number 17 will be here. The next number is 8 and the modulo of 8 by 6 is equal to 2. So we already have the number 2 occupied the location of location 2. So we are adding this one to the end of the linked list that we have here. So also the last item or the last key is 4. So 4 will be the modulo of 4 by 6 is 4. So we are inserting 4 here. Okay. So that's the concept of like the open hashing or the separate chaining. And as you see, like one way is to implement it using the linked list and inserting to the item here. So one thing about the separate chaining and look at this one, the values at this index 2 and 8, and as you saw at first, like what we did was we inserted 2, then we added 8. But one better way, okay, might be like for example sorting them based on the key values. So here the key 2 has a lower number compared to 8. So it was possible, like for example, when you're inserting number 8, then because 8 has a like the higher key or the greater key, so we could like put 8 at the first of the list and then put the 2 at the second, like the second location. So like if we had sorting, okay, so it's gonna be 8 then 2. This way, if you're looking for a key, okay, because the numbers are sorted, then it's easier to find the location. Similar to what we had also here. We had keys 5 and key 17. So if we had sorted this one, okay, from the largest key to the smallest key, then we could have 17, then number 5. Now let's take a look at the insertion, deletion, and search operation in open hashing or separate chaining. So if we said that the number of items that are already in the table is equal to n, and also we have m, that is the size of the table. So if the distribution of the data that we have is uniform, so like the almost we have n divided by m numbers for every in every location of the hash table, then the insertion will be in the linked list gonna be the big O of 1, if we're assuming that we are adding at the end of the linked list and not sorting the items. If then the deletion and also the search operation will be both from the big O notation of n divided by m. And the reason is obvious, because every location has only n divided by m numbers, so the linked list size will be n divided by m. But the worst case is then when you have like the data that you have are not like the uniformly distributed, and for example you might have some location of your hash table that contains a lot of data, let's say close to m. So in some item, like the number of items you have is very close to the n that you have, the total numbers. So then the search operation, also the delete operation, will be the big O notation of, let's here write it, big O notation of n. And as we said, n is when almost all like all the values you have, this is the worst case, all the values have are all inserted in a same linked list, which is one linked list. So it's going to be from the big O notation of n for the deletion and also for search. We talk about the time complexity for the search and delete operation that was like in like the big O of n divided by m, okay, in average, and what the worst case for a big O of n. But let's take a look at like the values of n and m. So if n is much larger than m, okay, so it means that this value n divided by m is a very big number. So it means that the speed is very slow. Okay, speed is slow because this number n divided by m is a large number. So it takes more time to, for example, to search for doing the search operation. However, if n is much less than m that we have here, okay, so it means that the table size is really huge. Okay, so we have a very big hash table, but the number of items we are inserted are really small. So it means that we haven't used the memory wisely, because we have plenty of spots that probably are empty. So it's like the trade-off between the speed and memory. So again, if n is very big and like the m is not, then we have the poor speed. If n is small and m is very big, then we have the poor memory usage.